The fastest way to break a multi-tenant app is messy retrieval boundaries. We'll set up Pinecone namespaces and filters so tenants never bleed into each other. If your search returns another customer's documents, you have a real problem. Today you will learn a simple pattern to avoid that. After this video, you will know how to separate tenant data, tag vectors, and enforce filters so queries only return allowed results. No heavy math, just clear plumbing and practical rules you can apply to real systems. I'm Professor Pi, teaching search and IR from basics to advanced with simple concepts-first Python that helps you solve bigger real-world problems. Multi-tenant retrieval is a common pipeline problem. You index millions of vectors for many customers. Without clear boundaries, a single misrouted query can expose confidential data. Success here means predictable isolation, simple routing logic, and filters that reduce results to the correct subset. Pinecone gives two primitives that map nicely to these goals. At a high level, namespaces act like separate shells inside one index. Metadata filters are labels on vectors that let you narrow queries by attributes like tenant ID, document type, or language. Imagine tenant alpha and tenant beta each storing product documents. Namespaces keep their vectors in different shelves. Filters add an extra guardrail inside a shelf, for example enforcing that only vectors with tenant alpha tag can be returned. We will build a little demo that creates a shared Pinecone index, writes vectors for two tenants into separate namespaces, queries in a namespace to avoid leakage, then adds metadata tags and runs filtered queries. Finally, we wrap queries in a small router that enforces tenant and filter rules. Now we start with the initialization. This snippet initializes Pinecone and creates a multi-tenant index. It shows the basic setup you need before storing any vectors. Top lines create a client connection, and then check or create an index with a chosen metric and dimension. The snippet usually sets a dimension that matches your embedding model, and a metric like cosine for similarity. You also see the call that creates the index name. That name is the single shared store that will hold vectors for many tenants. If you change the dimension to match a different embedding model, queries will stop matching and you will need to re-index. The point is a single index, many namespaces. Now we will upsert vectors for two tenants. This snippet upserts one vector into two Pinecone namespaces. It writes the same toy vector twice and places it under two different namespace names, one per tenant. The code shows the basic upsert pattern with an identifier, the vector embedding, and optional metadata. You can spot the namespace parameter being varied between the two calls. Upserting into separate namespaces ensures each tenant's vectors are isolated at write time. If you instead used the same namespace, isolation would vanish. This snippet uses one small vector per tenant for clarity, but the same logic scales to many vectors by batching the upsert calls. Next, we query within a namespace to show isolation. This snippet queries Pinecone within a namespace to prevent leakage. It runs a similarity query against the shared index while specifying a single namespace, and then inspects the returned matches. The core idea is that Pinecone will only search the vectors stored in the named namespace. The snippet demonstrates sending a query vector, a limit on results, and the namespace string. You will see that results correspond only to that tenant's upserted vector, and not the other tenants. If you remove the namespace parameter, results would come from the entire index and could include other tenants. So namespace is the primary isolation control at query time. Now, we add metadata and use a filter to narrow results. This snippet adds metadata and queries Pinecone with a filter. It shows inserting a vector with keys like tenant ID and document type, and then running a query that supplies a metadata filter expression. The snippet walks through how to set metadata fields on write and how to phrase a filter to require a matching tenant ID or category on read. Filters let you implement rules, such as only returning vectors that match a tenant tag and an access level. If you add more metadata, like language or region, you can combine conditions to get more precise results. Filters are slower than pure namespace isolation, so use them when you need fine-grained control inside a namespace. Next, we wrap queries into a tenant-aware function. This snippet wraps Pinecone queries for tenant routing and filter enforcement. It defines a small router function that accepts a tenant identifier and a query vector, then enforces which namespace to use and which metadata filter to attach. The code shows the decision logic up front, mapping a tenant to its namespace and required filter. Then it calls the Pinecone query with both namespace and filter together. Wrapping queries in this way centralizes routing rules, reduces the chance of developer error, and makes audits straightforward. If you later add multi-role permissions, that logic is the natural place to combine role checks with filters before running the query. If you map this toy flow to production, you keep one index per embedding shape, create namespaces per tenant, and attach tenant ID metadata on every upsert. The router lives in the service layer and is the only component allowed to call Pinecone.
That keeps audit trails and simplifies rotation of keys or schema changes.
Recap. What it is: a pattern using one Pinecone index, namespaces for tenant separation, and metadata filters for extra guards. When to use it: when multiple customers share a vector index and isolation plus flexible filtering matter. One caveat: filters cost a bit of query overhead and are not a substitute for clear namespace boundaries. Wrap punch. Next step: scale and evaluate this same setup. Increase your corpus size, switch to an approximate nearest neighbor setting in Pinecone, and add timing and accuracy checks to measure latency and recall as you grow. If short, practical IR helps, subscribe and watch the IR videos.